Good morning. Welcome to Currents World. In this video, let us discuss NERNST'S distribution law and its deviations. What are their applications? Okay. Let us take a beaker and add two immiscible solvents A and B. There are two solvents in a beaker. These two are immiscible with each other. That means they are not soluble in each other. So they form two separate layers, two separate phases, as you see here. Now add a solute X to it. This solute is soluble in both A and B. A is soluble in both A and B. It gets distributed between or partitioned between A layer and B phases. Fourth point, X, the solute molecules move from A to B and B to A, vice versa. At equilibrium, the rate of forward movement is equal to rate of reverse movement of solute molecules from B to A. Okay, so at equilibrium, rate of forward process is equal to rate of reverse process. Now let us define NERNST'S partition law or NERNST'S distribution law. It is also known as NERNST'S distribution law or NERNST'S partition law. It states that if a solute distributes itself between two immiscible solvents at constant temperature, then X is in the same molecular state in both the solvents. Okay, then the ratio of concentration of solute in A to ratio of concentration of solute in B is equal to constant. That is C1 by C2 equal to constant. This constant is called partition coefficient or distribution coefficient, or it is also known as distribution ratio. Okay, since the solubility is also represents the concentration, more the solubility, more the concentration in the two layers. So solubility is nothing but concentration. The distribution law can also be rewritten as C1 by C2 equal to S1 by S2 equal to K. That is, S1 and S2 are the solubilities of the solute in two solvents. Okay, now let us see the limitations of the NERNST'S distribution law. What are the limitations? The law is valid when the molecular state of the solute is same in both the solvent. The molecular state should be same. Okay, and if the solute undergoes association, for example, benzoic acid in benzene layer undergoes dimer formation, and acetic acid in aqueous layer undergoes dissociation. Okay, then in such cases, the distribution law is no longer valid. So we need to modify the NERNST'S distribution law. Okay, we need to modify the equation. The solutions are dilute. Both the solutions are dilute. It should not be more soluble. The two liquids are mutually insoluble or very sparingly soluble. For example, benzene and water, they are completely immiscible. Their mutual solubility, and then by adding solute, the mutual solubility should not increase. The mutual solubility should not be altered by the addition of solute. The distribution law can be applied after modifications. In dissociation or association case, we will see in the next slide. There are two deviations or modifications of NERNST'S distribution law. They are 1. Association of the solute in one of the solvents. The solute undergoes association. For example, benzoic acid in benzene layer undergoes dimer formation. So the NERNST'S distribution ratio K equal to C1 by nth root of C2, okay, where C1 is the concentration of solute in the phase 1 and C2 is the concentration of solute in the phase 2. Okay, for dimer, let us put n equal to 2. For dimer, n equal to 2, therefore C1 by square root of C2. For n equal to 3, for solute undergoing trimer, then C1 by cube root of C2. Okay, if it undergoes n, then nth root of C2. The second case is dissociation of the solute in one of the solvents. In this case, K equal to C1 by C2 1 minus alpha, where alpha is the degree of dissociation. It is the fraction of the solute dissociated. Therefore, it is the NERNST'S distribution law is applicable for solute in unassociated or undissociated form only. Therefore, C1 is the concentration of the solute in phase 1 and C2 1 minus alpha is the concentration of solute in phase 2. Okay, let us discuss and derive the equation association of the solute in one of the solvents. Okay, let solute molecules are associated or undergoes association to give NHA reversible arrow HA n times, where HA is the solute which undergoes association. For example, benzoic acid 2 times gives dimer. It will be associated to give dimer in phase 2, whereas in benzene layer, in water layer, it is C1. Okay. The associated molecules will exist in equilibrium with the unassociated molecule. The associated molecules will be in equilibrium with the unassociated molecules. Okay, let C1 be the concentration of the solute HA in phase 1 and C2 is the total concentration of HA in phase 2. Okay, let us apply the chemical equilibrium to obtain the K value. Okay, let us write in reverse direction. It is nothing, equilibrium only. HAN gives reversible arrow NHA. Therefore, by applying law of chemical equilibrium, the equilibrium constant is equal to HA to the power n, concentration of HA to the power n divided by concentration HAN. Okay, subscript n. HA superscript n, okay, cross multiply. So, K into concentration of HA subscript n. Then, okay, let us take nth root. Okay, so here concentration of HA nth root. Okay, this one. Next, as in benzene layer, benzoic acid is fully associated, mostly associated. Therefore, as HA largely associated in phase 2, then C2 equal to this only, not this. Therefore, C2 equal to HA, concentration of HA, dimer, concentration of the dimer only, C2 equal to. Okay, so let us substitute in this expression C2, HA. Okay, so HA equal to nth root K. Okay, HA, instead of HA you put, let us take K outside, K prime, so square root of nth root of C2. Now the distribution law is valid only for unassociated solute molecules. Okay, unassociated, only the molecules in the same state in both the phases. Therefore, K equal to C1 divided by concentration of HA in phase 2. Therefore, HA equal to C1 divided by nth root of C2. For benzoic acid, N equal to 2, therefore C1 by square root of C2. Okay, let us consider the second case where dissociation of the solute in one of the phase, one of the solvent. Let HA dissociates in phase 2, but not in phase 1. Let C1 be the concentration of the solute HA in phase 1, and C2 is the total concentration in phase 2. The distribution law is only valid for the ratio of concentrations of similar species, not for this species. Similar HA. So undissociated. The distribution law is valid for the ratio of concentrations of undissociated similar molecular species in the two solvents. Then therefore HA is a weak acid. For example, acetic acid in aqueous solution, it undergoes dissociation, partial dissociation or ionization, where alpha is the degree of dissociation. It is the fraction of solute dissociated, therefore 1 minus alpha. We have taken C2, total concentration C2 in here, therefore C2 1 minus alpha, C2 alpha. K equal to concentration of HA in undissociated. This is undissociated, and this is the undissociated will be C2 1 minus alpha at the equilibrium. Therefore C1 by C2 1 minus alpha, where alpha is the degree of dissociation of the solute in phase 2. Okay, we can calculate, if we know C1, C2, K is a constant, then we can calculate the degree of dissociation, or if we know alpha, C1 and C2, then we can calculate the NERNST'S distribution coefficient. Thank you for watching. Please share and subscribe. Thank you very much.